All right, everybody. This is going to be pretty short and sweet for a couple of reasons. Number one, I'm exhausted, as I'm sure you are. Number two, the problems in 2.1 are not that intense in terms of how much work goes into the problems, at least for the first problem set. So we're going to look at two different example problems. The first one here is from Chapter 8, number 38, parts A, B, and C. There is a D and an E part to this, but I'm not going to look at those. I'll let you tackle that on your own. We will look at these first few here. The instructions tell us to indicate the bond polarity, show the partial positive and partial negative ends in the following bonds. Okay, well, in order for a bond to be polar in the first place, there has to be a moderate difference in electronegativity between the two atoms that are participating in the bond. If the difference in electronegativity is small, or 0, for example, then there is not going to be any bond polarity. But if there is a difference, it's kind of hard to pinpoint a number. You could think of like if the difference is like more than about 0.5, then that's usually enough. Then you could say that it would be a polar bond, and then you can assign the partial positive and partial negative ends. So let's first check to see whether any of these bonds fit the polar bond or polar covalent bond category, and then if they do, we'll talk about how to assign the partial positive and partial negative ends. So what I need to do is I need to go into Canvas here and pull up the electronegativity table. So you can find that in the top module on Canvas. Okay, here we go. So the first bond was between carbon and oxygen. Carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. The difference here is 1. I would consider that moderate. Like I said, if you have a difference of 0.5 or greater, that's kind of the cutoff. It really does depend on more than just the electronegativities, whether something truly is polar or not. You know, for example, there may be a situation where something that has a difference of 0.4 might act kind of polar, and something that has a difference of 0.5 might not. There can be some other things that go into play. But generally speaking, if the difference greater than 0.5, then we would consider that to be polar covalent. So this difference of 1 means that the carbon-oxygen bond is definitely going to be polar. And the way that you can assign the partial positive, partial negative is by looking at which element has the higher electronegativity. Oxygen is more electronegative, meaning it pulls harder on the electrons. Electrons are negatively charged, so in this bond between carbon and oxygen, the electrons that make up this bond are going to spend more time with the oxygen, okay, because it is more electronegative. So the partial positive, or excuse me, the partial negative region of this bond would be on the oxygen side. The partial positive region would be on the carbon side, okay? And we're just going to be applying that exact same principle here to parts B and part C. So let's look at phosphorus and hydrogen. Phosphorus has an electronegativity of 2.1. Hydrogen has an electronegativity of 2.1. These have the same electronegativity. What that means, right, is that neither of the elements is better than the other at pulling on electrons. They're sort of, it's a tie game in the tug of war. But on these electrons here in the middle that make up the bond. So there's not going to be any partial positive or partial negative regions along this bond. The negative charge of the electrons is equally distributed here. Okay, let's look at hydrogen and chlorine. Something tells me we are going to have a polar bond in this case. Okay, so 2.1 versus 3.0. That's a difference of 0.9. We'll go ahead and say that is a polar covalent bond. And chlorine has the higher electronegativity. So chlorine would get the partial negative, and or I should say chlorine is partially negative and hydrogen is partially positive in terms of the bond there. Okay? I'll show you guys in class on Friday how to actually write that partial positive, partial negative. You can see it in the book on some of the questions. I think like question 37 shows it's a little sort of, I don't know what that symbol is. I think it's like a lowercase sigma or something. I'll show you how to write that specifically, but that's how you denote that it's a partial negative charge and not a complete negative charge, like just writing +1 or +2. It's just partial. So, okay, the next problem that we're going to look at is trying to interpret what's going on in these. These are supposed to be like three-dimensional visual graphics of electron density. Okay. So I mentioned this during the video. There's another picture that I show in the video for the notes. The red region represents an area that is electron dense, and the blue region represents an area that is not electron dense. Okay, what this means essentially is that the red areas are slightly or partially negatively charged, and the blue areas are not. They're the opposite, so they're partially positively charged. Okay. So this is asking us to state whether or not each of the following has a permanent dipole moment. Okay, this clearly does. This would be a negative end and a positive end. Okay, that's what it means by a dipole. And it is permanent, okay, as you're going to see down here, some of these cases are not. It's permanent because this is non-symmetrical, okay? So like, it's clearly negative over here, clearly positive over here, and that's not going to change. Like, it's not, it would be best to go to part C, okay? So let's look here. In part C, we still do have like blue and red regions, but there's symmetry, right? So we've got like positive on the end here, positive on the end here, and then negative in the middle. And then it looks like maybe kind of getting towards a positive in the middle as well. Overall, there's no permanent dipole moment, and you really just want to be thinking about the symmetry of things. This looks like it's probably some sort of molecule that's like, I don't know, 2 oxygens or 2 nitrogens together, something like that, where the electron density is actually just like around the atoms itself. I'm not exactly sure what this is, but because there is the symmetry here, we would say that there is no permanent dipole moment. There may be temporary dipole moments, right? We do see there is probably negative and positive regions, but overall, the molecule does not have permanent dipole or polarity associated with it. Now here for part B, if you want to look at this problem in the book, it's on page 353A. It's letter B in number 43. This is supposed to be a 3D picture, and I believe this is supposed to represent like a molecule of methane, which in 3D adopts a tetrahedral shape. So there's a blue region sort of off to the left that's sort of pointing away from us that we don't see, along with a matching region over here that's pointing away from us that we don't see. And then we have these 2 blue regions here. This is another example of sort of symmetrical dipoles that sort of counteract each other. So there's some negative regions sort of in the middle here, and then positive regions on the end. Overall, there's no permanent dipole moment because of the symmetry here. We're going to learn later on in this unit more about the shapes of molecules. And so I think it's a little bit unfair to expect you to be able to talk about like these 3D shapes. A little bit easier for like A and C, right? It's pretty easy to see the difference in symmetry there. For B and for some of these others, if it looks like it's trying to represent something in 3 dimensions and you can see where the symmetry is, then, you know, we'll just try to take it as it comes. Like I said, later in the unit we will learn more about 3D shapes of molecules, and then we'll be sort of reapplying this concept at that point. Because what does happen in reality is that molecules that do have polar bonds will not act like a polar molecule if those polar bonds are offsetting each other due to some symmetry. So for example, the carbon-oxygen bond, we said that this was polar, right? Oxygen is partially negative, carbon is partially positive. Well, let me show you carbon dioxide, okay? So here's a nice little picture of carbon dioxide. This is nice and symmetrical, right? So overall, this is not going to have a permanent dipole moment, even though the individual bonds are polar. Okay, so once again, it's just that symmetry that you're trying to find. Okay, all right. Well, that's it for this video. Like I said, nice and short. Hopefully, you guys have a nice day, and I'll see you in class on Friday.